And I make one more lemma, which is if R is prime and L is a left ideal of R, and small of L, this is the set of all elements in R which with the property that L multiplied by R equals 0, so this is the right annihilator of L. Then the statement is that, and the ring is, okay, the ring is prime, is the intersection of the right annihilator of L with L. Then this is a two-sided ideal of L, and L modulo M okay, this is L modulo M is prime. So maybe it was better to write that this is two-sided prime ideal. Yeah. So the proof is, first of all, we want to see that this is an ideal, but you see, if you have, so we want to show that, of course, if you have Lm, this is contained in L with and RL, and of course this is zero because this is the right annihilator. If you have ML, this is contained in RL, and since L is a left ideal, this is contained in L because L is a left ideal of R. So this is really M is a two-sided ideal of M. The easiest part. And now we want to say, to take two ideals, we take I and J, two ideals of M, with the property that their product is inside M. And we want to show that one of them is inside, they are two-sided ideal of M, we want to show that one of them is inside M, if we know that their product is in M. So now, this is, we do the following way. We take I and multiply it from left by L, and also we take multiply this from right by R. And I claim that this is an ideal of R. So the proof, this is clear that L is an ideal, so if you multiply from right from left, you get something. If you multiply here from right, this guy goes here. So this is obvious. And similar for the other one, you have Lj plus Ljr is also an ideal of R. So if you take the product of these two ideals, so we take the product of these two ideals, Li plus Lir times Lj plus Ljr. So here the problem is that since we don't know whether we have one or not in the ring, we need to write this way. If we have one, so you don't need this because. So here, this thing is, if you write down, this is Li Lj plus Li Ljr plus Li R Lj plus Li R LJR. So here what we have, we know that I and J, the product is inside M. So here we use that, here we have this group, okay. So I want to prove that this thing is inside I want to show that this is 0. If I show that this is 0, then I have that the ring R is prime, so I should conclude that one of these objects is 0. But the problem is how to prove that this is 0. For the first thing, we have L, so we have L, J, I simply L, I, L, J. So you see here, I and J, they are ideals of L, and J, of course, this is also, so this is an I and J, they are ideals of M, so this is inside J, and we already know that the product of L and J, so this is inside LJ, L, I, J, and IJ, this is, by definition, this is in M, so this is in LM, and we know that this is 0 because M is inside R, the right now later. So for this part, this is 0. For the next part, we still have that this part here is 0. So we have similarly Li, Lj, R is 0 because this part is 0. Here we use that this is inside L because L is a left ideal, and we have similar arguments. So all these things, they are equal to 0. So we simply have that the product of these two ideals is 0. So since R is prime, this simply implies that Li plus Lir equals 0, or Lj plus Ljr equals 0. Is something wrong? Or? Okay, here you see, if you write these ideals, you simply take an element from here and an element from here. This element is a linear combination of elements of this kind, something from L, something from I, something from L, something from I multiplied by something from R, and I write this in this way. So here you have this group here and here. If I show that this is 0, this also should be 0, of course, because you multiply from R. Here I know that R times L is inside L because L is a left ideal. So here I have the same group R, I, L, I, L, J as here. Here we have something similar. This is inside L, so I have L, I, L, J. So if I prove that this is 0, everything should be okay. And here you simply put, we use that J is an ideal of L. And so this is inside J, and you have Ij, this is in M, by assumption, and you get simply that this object is inside Lm, but M annihilate L from the right, because M is a part of the a part of the you have unaggregated. So this is 0. So all these elements are 0, and we have two ideals in the ring R, which is prime, and the product of these two ideals is 0. So the conclusion is that one of these ideals is 0. So this is in the moment. So one of these ideals is 0. So this implies that the elements L here, this implies that, for example, Li equals 0. And this means that I is inside L, but also I is inside the right annihilator of L. Because the first thing is because I is an ideal of L, and the second one because if you multiply the elements from L by elements of I, you get 0. So I is in the right annihilator. So this means that I is inside M. And it was the definition of prime ideal. If you have a product of two ideals, one of them is inside. But this is some exercise which you see, this is something which is maybe not to be recorded, but when I was a student I had the feeling that all structure theorems in theory they are isomorphic, or at least the proofs are isomorphic. And in my career I avoided up to now structure theorems in my courses, but here I made an exception. So, but this is something which, okay, this is, I'm sure that I am not correct. That not all theorems are isomorphic, but maybe my teachers presented them in such a way.
During the proofs or the
Okay. Okay, this is something like a magic. You do something, you put something, and finally you get the proof. And what is here inside? But in order to be honest, in associative algebra, I think that the structure part is the leading part. So